Yes, or no, wait, sorry. I was clicking. So FCB is not in compression, FCB is in tension. So think about this. We drew FCB pointing to the left, right? Pulling on point C. So just like the rubber band, right? This is FCB. FCB is in tension. It's pulling. Well, we drew it pulling on C, right? Now, when we set up the equations, we've got this one we know is pointing to the right, right? We mathematically express 15 kilonewtons positive, FCB is negative. When I solve the equation, I wind up with a positive number. So that means I chose the right direction. Now, this one is fairly intuitive to look at and say, okay, if I'm pulling to the right over here, in order to maintain static equilibrium, I need to pull to the left over here. So you can see we chose the right direction, by default. So this is definitely under tension. And then we do the same thing for the Y direction. And here, up is positive. This is my notation for, so what do we have? We have 8 kilonewtons acting upward minus FCE acting downward. So this one is also straightforward. We've got FCE equals 8 kilonewtons. And I'll give you guys one more chance. Is this one in tension or compression? Problem with the chat is I can't see when. Oh yeah, there it is. Okay, so no one answered this one yet. Yeah, you feel free to type it in the chat. Compression. FCE. This member FCE, is it in compression or tension? All right, I got 2 compressions. All right, this is actually in tension as well. So same thing applies, right? This member is pulling on point C, right? So let's look at this, well, up here. All right, this is the structure. The force on point C is downward, right? That means the member is pulling on point C. That means the member itself is in tension. It's been elongated like a rubber band. So what does it want to do? That member itself wants to pull back together, right? So it's exerting a force on C, downward. The member itself is in tension because it's stretched and it's trying to pull back. So I think this seems like one of the most confusing parts of method of joints, or just structural analysis of the trusses in general. When you start off, is figuring out, are you in tension or compression? And there's a bunch of ways. I mean, the most rigorous way to do it is just looking at the signs, right, as you do your math. I drew it in tension. I got a positive sign, so it is in tension. Let me move on to the next joint, and hopefully things will become clearer. I could make a joke about joints here. All right. Okay, so now what do we got? We've got, if we look at our problem, we know this force, we know this force. We can go to joint B now because we've got 2 knowns and 2 unknowns over here. So I'm going to switch over to that. Let's look at, let me write right here, 6.9, continued. Joint B. All right, Let me draw joint B out. So I've got joint B, and let me draw what we know in red. Or maybe I should just, yeah, I'm going to draw. So we're going to draw everything acting on joint B in tension, unless we happen to know what it is and it's not in tension, right? So we don't know the one that's acting downward from B to D. I should draw that in regular blue pen. And we don't know this one, FBE. Let me get the diagram going. Right, we don't know FBE. Well, we do know BC and AB. AB, so this is another point of confusion for people. Be careful. Joint A, at joint A, the force AB is pulling on A, right? Because the member itself, FAB, is in tension, right? So if this member is in tension, it's being stretched, right, by the forces that are acting on the entire structure. So it wants to pull on A, and it also wants to pull on B, right? So this member's in tension, which means it's pulling on the joint. So I'll draw this over here. This is 15 kilonewtons. And this is, I'm just going to write down FAB. So we calculated FAB in tension. It is in tension. It's pulling on both joints that it's attached to. That's why we drew it this way. Oh, let me label this joint B. All right. The other thing we have is joint BC, which again, we just calculated. Or joint, member BC. We've got the same situation here. A BC or CB. So that's the other part of this. When you draw a vector, you typically draw it from, or you have the notation from where it's going to where it's going to. So BC, BD, right? BE. Over here, it's CB. So remember, CB and BC are the same member. CB is 15 kilonewtons, and that's in tension, right? This member is in tension. So BC is in tension, right? Same as A, it's being stretched by the loads on this structure. And because it's being stretched, right, it wants to pull back in. And it's not just pulling on one end, right? It's pulling on both ends. So it's pulling at C and it's pulling at B. So it's the force at the joint itself is directed inwards. It's in tension. BC. And this is also 15 kilonewtons. Right, so we calculated those. And notice we calculated those independently, right? We looked at joint A, we looked at joint C, we calculated those. But now we have joint B stuck in the middle. Now, let's look at what's going on here. The sum of the forces in the x direction is equal to 0, right? And that's, this way is positive. What do I got in the x direction? Well, I've got 15 kilonewtons from BC. I've got 15 kilonewtons from AB. I'm gonna make a little note up here. Now, I'm going to write this out because it's worth demonstrating. FBE is a triangle, right? If I look at the triangle that this is made up of, I've got, you know what, I'm going to draw it over here. What do we got? 1.6 and 3. This is 3.4. Oh, I drew this right where I need to write. All right, so let me add it over here. The force from BE is the x component, right, is the same as the ratio of the distances for that triangle. We already discussed this for joint A. That's where the 3.4 came from, right? Just Pythagorean theorem. So the force in the x component is just the force of BE. And notice I put it a plus because it's pointing in the positive. The components of this are positive x, negative y, right, for the FBE force. But the ratio is going to be 3 over 3.4, right? But look at my equation. I've got 0 equals 15 minus 15 plus that. Well, if I solve this, I basically wind up with FBE equals 0, right? And I don't have to ask you if that's in compression or tension because, yeah, it's not anything, right? It's a 0 force. So this is a 0 force member. This is what the book tells you to look out for. And it's really it's not something that's necessarily easy to figure out by looking at something, looking at a structure until you've had some practice. So let's look finally at the sum of the forces in Y here. Remember, FBE is 0. So there's no Y component of force there. So all we have is we've drawn negative FBD, but there's no other Y components of force. So this just means that FBD equals 0 as well. Those are 2 0 force members in the structure. Let's see, is it good? Let me see if there's a slide. I thought there was a slide with the rules of 0 force members. Yeah, here's one. No, this is not 0 force though. 0 force is right here, I guess. And this is not obvious because it's not 3 members. I think that's one of the confusing parts about the 0 force member for this particular joint. But the point is that even if you don't recognize 0 force members, you should be able to discover them as you're doing the math, right? So don't panic if you get an answer of 0, but you can go back and look. Oh, let's see, I got a question. FAB, oh, sorry, let's see. Yeah, this right here, yes, this is FAB. Oh, that, Alex, was that your question right on this problem? Kilonewtons. Oh, up here. This is tension. Yeah, I underlined it for some reason. 15 kilonewtons tension. hopefully I answered that question in the chat. All right, so joint B is done. What are we going to go to next? Oh, look, joint E. We've determined this is a zero force member, right? We know this, and we don't know this one or this one. So let's go to joint E. Again, I sort of picked that arbitrarily. I'm going in order of my notes. You could have gone to joint D at this point. But let's look at joint D. Oh my God, between my pen and my writing, I can see why you guys are asking me all these questions about when I'm writing. All right. Again, feel free to shout out and ask, what the heck did you just write? Because sometimes even I can't read my writing if I'm going fast enough. All right, so let's draw joint E out. Let me bring the diagram in here again to the side. All right, joint E. All right, we've got joint E. Now I'm going to draw my unknown forces in tension, right? We only have figured out CE. Let's start with that because this is where we figured that out. Force CE, 8 kilonewtons in tension. So that means the member CE is in tension, right? It's being stretched, right? Tension means something's being stretched. Compression means something's being squished. So we're pulling this beam, we're stretching it out. So that means at joint C, the beam is pulling at joint C, right? That's why it's under tension. That means it's also pulling at joint E. So it's pulling upward with a force of 8 kilonewtons. What is this, EC? I think the big disconnect that you have to bridge is drawing and drawing the joints versus understanding how that force translates in the member, right? What's the force on that joint indicates if the member's in tension or compression. You just got to think about, okay, if it's pulling on the joint, that means the member's in tension. If it's pushing on the joint, that means the member's in compression. And we're going to draw all these other unknowns in tension because that's sort of the rule. Now I'm going to put BE in here as a dashed line. All right, so what do I have? I have force ED. If I fix this, it's just going to look worse. Oh, there it goes. Force ED. And this is force EF. And up here we've got 0, right? This is force, what was it? B. Remember, force BE was a 0 force member, right? We calculated that above, but I'm just drawing that in there just to show that it's 0 but not forgotten. All right, so this one is again fairly straightforward. We're going to write out the sum of the forces in Y equals 0. I'm starting with Y because I've got this one and this one. It should be kind of obvious from inspection what everything is on this. Now, you're going to have some joints like this where it's obvious, right? But I want to at least go through the equations so you realize. So in the positive Y direction, right, I've got 8 kilonewtons. And then I'm subtracting the force EF because I've drawn it in tension away from E. Force EF equals 0. So when I solve this, right, I find that the force EF is 8 kilonewtons, and I chose the negative. I chose the negative direction. I drew it in tension. I accounted for it acting in tension. I have a positive number. It is in tension. That's tension. And then the next one is sum of the forces in x equals 0. And I think you can see where this is going. What do I have in the x direction? I've got basically just FED, right? But that's acting in the negative direction the way I've drawn it. So all I have left is that FED is equal to 0. 0 what? 0 anything. It doesn't matter if it's kilonewtons or pounds, I'll put kilonewtons. All right, that's joint D. Or, oh, geez, I'm sorry, guys. I wrote joint D and I did joint E. There's one disaster after another with that label. Joint E, yeah. Oh my God. This is, yeah, that's D over there. All right. These are correct. EF, ED, this is joint E. All right, now let's go on to joint D. Now, joint D would be a little more complicated if you didn't know a few things about the other forces, right? Let me draw joint D here. Draw the point here. I'm going to draw these in as dashed lines again. Remember, this is force dB, and that's equal to 0. And this is force dE. Oh my God, and that's also equal to 0. I've got so much paper here, and yet I insist on writing so small. I've got this fear of running out of room. My parents used to make me redo my math homework when I was a kid because they couldn't. I would try to fit everything on one side of the page, and then they would like, I can't read this to check it. Or, what does it say? Write it bigger. All right, enough about my my abusive upbringing. All right, we've got dB and DE here, which are both zero force members, right? But we've also got AD and DF. So I'm going to draw the lines here, and then we'll figure out which direction they need to go. All right, that's what it looks like. F. I'm not even going to label them, I guess. All right, let's look at AD. Joint AD. We figured out joint AD was, I'm just going to cover it up, 17 kilonewtons in compression, right? So again, that means at joint A and at joint D, this member between them is being compressed, right? So it's being pushed together. I don't even have, I should have looked for a spring. All right. So the joint's being pushed together. The beam itself is trying to resist that compression, right? And it's got some elasticity to it. I know it's kind of hard to imagine elasticity in a steel beam, but all ductile materials have some sort of elastic region they operate in. And you're going to learn that in, what is it, 219, mechanics of materials. So if you push on the beam and compress it a little bit, the beam's going to want to push back, right? So we already know at A it's pushing on A, right, up here. So it's pushing on D. Let me draw A in so you don't get confused, right? This member is pushing on D. So this over here is 17 kilonewtons in compression. Oh my God, this is I should have drawn these in red. I forgot I used red for the known forces. All right, now there's a few ways I can do this. I'm going to do this mathematically for you, but I think what you can see, I want you to see this first. These are zero force members, right? There's no force. D has a force acting on it in compression, right? It's pushing. This beam is pushing on point D. In order for point D to stay where it is, this has to be pushing back on it. These have to be equal and opposite in forces. These are the only two members left, right? Everything else is zero. But I want to draw this out mathematically for you so you can see how we would draw it in tension, right? I'm going to draw it in tension, and let's see what happens with the numbers when we do the math. So let's do sum of the forces in X equals 0, right? So I'm looking at these two. Ignore this arrow up here and this point. This arrow is pushing. I've got this drawn in tension. Now, obviously, you're an expert student in statics. You're gonna be like, oh, this is impossible, right? This has got to be pushing in that direction. But for the sake of argument, I want to show you how, assuming tension when it's actually in compression, right? I want to show you that again because it seems to be a point of confusion for statics. All right. So the sum of the forces in the X direction. I'm going to take, this is the positive X direction, and what do I got? Well, I need to put some dimensional numbers in here for my triangle. Let me look at my triangle. It's going to look like this. I've got 3, 1.6, 3.4, and I've also got the same thing down here, right? Three, 1.6, 3.4. This is like, you know, this is just the geometry. A, D, F, right? Those are the triangles. So I can break my force down into X components. I've got in the positive direction, right? This arrow is pointing down and to the right. So the X component of that is pointing to the right. So that's going to be 3 over 3.4 times 17 kilonewtons. Now, I've drawn this force in tension, right? So as far as I know, as someone who hasn't analyzed this problem further, as someone who maybe hasn't thought about the physical aspect of what's going on, I'm just following the math, right? And following the math tells me, oh, you know, I drew this pointing in that direction. My X component is pointing in the positive direction. So I've got, oh, I didn't even label this. This is force DF. I've got force DF times the ratio, same ratio, 3 over 3.4, right? I can rearrange this equation, and I can solve for FDF. So I'm going to have, on one side, I'm going to have FDF times its ratio, 3 over 3.4. Now notice I have to subtract one of these because I've got it equal to 0. So I'm subtracting 1, bring it to the other side, equals 17 kilonewtons times 3 over 3.4. All right, now just simple math, right? These all cancel. And I've got, look, FDF is equal to negative 17 kilonewtons. So now I say, well, wait a minute, negative. I drew it in the positive direction. What's going on? And here I just tear up my paper and give up. No. So here I say, oh, okay, well, I must have chose the wrong direction. So FDF is really 17 kilonewtons. Oops. Oh my God. All right. Scratch that. FDF 17 kilonewtons. And it's not in tension, it's in compression. So really it looks like this, right? Joint D looks like this. It's got the point D. This is F DF, and this is F. Well, I guess technically it's FFD, right? Because it's pointing from that direction, right? It's pushing on point D because it's in compression. The beam itself is in compression, so it pushes on point D. Or you say, I reverse this, I drew it in tension, it's actually negative, so that means it's in compression, it's pushing on point D. So hopefully going through that at least got you to see again how you can do it mathematically and not have to intuit compression or tension, but you need to at least know what it means, right? When you draw an arrow, I draw an arrow away from point D. That means I think this member is in tension, it's pulling on D. But oh no, my math came out backwards. So this is telling me I've reversed the direction. So it's actually pointing back towards D. All right. Oh wow, it's 12:42 already. We have a little bit of time. Are there any questions about this problem? Method of joints. No, nothing in the chat. All right, let me flip problems here. And find my, oh, here it is. Huh. I don't know if we're gonna have enough time to do this. Well, we definitely won't have enough time to do the problem. Let me just see how far we can get. All right, problem 619. Let me grab a screenshot of it because screenshot tool. There it is. Come on. Screenshot tool is still starting. Come on, where is it? Oh, here it is. Put this in the chat. All right. So that's the picture in the chat. What I want you guys to do, in fact, you know what? I'm not even going to do breakout groups. Just sit down and figure out. In fact, I can just leave it up so it doesn't matter that I got a screenshot. The first thing I want you to do is draw yourself a free body diagram and figure out what are the reaction forces at A and the reaction forces at H. And my hint here, well, not my hint, but you can see H is on a roller. So there's only going to be a vertical force. And you should recognize that, I mean, when you draw your free body diagram, you're going to draw an X component. But in solving this problem, you can see that there is no X force acting on this structure. So, right, all the forces, the sum of the forces in X are 0. So I'll just give you that one. Because I put together a poll here for you guys to answer. Report the vertical. So when you're done, go into this poll and answer the question as shown. Report the vertical forces at A and H in the format AY equals Q kips up or down, HY equals R kips up or down. So you're going to get something like if AY was 100 down, right? You'd say AY is 100 kips down. HY is whatever, 100 kips up. I don't know. So let me put the picture. Is the picture on here? No, I deleted the picture. Oh, you guys have the picture on your capture. Let me see if I can overlay the picture with the poll. Got the picture. Got the poll. Ah, there we are. I'm not going to show the responses. Oh, yeah, this shows you how to join. All you do is you text. You can use the poll everywhere link up here, or you can just text D Sarajanis 556 to the number 22333, and then you text in your message, and it'll show up on the screen when I show the responses. So go ahead and figure out the sum of the forces, or the forces H, Y, and AY. Let me see if I can get my, there it is, my graphic up. I'll put this right here. See if we can get responses before, if not, we'll just start here on Monday. I'm gonna have to go through all this again. Maybe I should just have you test poll everywhere. You know what? We've only got 3 minutes left. Why don't we, let's test poll everywhere. Forget solving this problem right now. We're running out of time. What I want you to do is, this poll is open. Join the poll. I want to make sure everyone can join, and then just text in like, hi, I'm here, or yes, I've joined, or, well, obviously if you're not texting in at all, and we'll get responses like that. Oh, testing from computer, good. Yes. All right, so this is how the responses are going to show up. Now, I don't know if I can scroll once they've scrolled off the screen. Here, 1, 2, 3, 4. All the people from Thermo are like, oh yeah, we did this the other day. All right, we'll just use this time to make sure everyone figured out the poll. I am your father, yeah. Oh, okay, I can scroll, good. 1, 2, 3, 4, 5. Yeah, this is the problem with the free texting. People can write anything. They used to use this at our company. Well, they probably still do, but when I was at Praxair, they used to do quarterly meetings, and some big shot would come and give a talk to the site, and they'd use a poll everywhere to get responses from people, you know, for questions and stuff. And I'll tell you, it was a lot easier to ask a tough question when it was anonymous through poll everywhere than than to raise your hand and ask a question. Oh, Elon Musk has joined us. That's good. All right, so it looks like either I've got one person putting all these things up here, or most of you have figured out how to use poll everywhere. All right, so we'll pick up here on Monday. We'll start this problem. It's 6:19 in your book if you want to do it in advance. You can try it out and see how far you get. Oh, I keep forgetting to make the homework public. I got to do that, so I'll put the homework online as well. But at the rate we're going, it's not like it's going to be due on Sunday. So, all right, like I said, method of joints is not exactly the, it's relatively simple. It's just conceptually difficult for people to understand the first time they do it. It's like, what I drew it this way and it's that way. The compression and tension part throws people. All right, I'm going to deactivate this. So that's what I have for today. Yeah, there was not enough time to do that. I'll see you guys on Monday. Come prepared to solve the problem.